So in the previous video I introduced you to the concept of a latch, and a latch is something that allows us to store the state of a circuit so that we can reference it at a previous point in time. If you remember the SR latch that we talked about, there were some problems with it. There were certain states that did not work very well. They caused this issue of metastability, this undesirable behavior in our circuits. So in this video, I'm going to introduce you to a second kind of latch that can help solve that particular problem. And then we're going to take a look at an additional form of storage called a D flip-flop. So let's take a look at this latch first and try and solve that problem that we had with the SR latch. Now the first thing I want to point out to you about this new latch that we're calling a D latch is over here on the right hand side. You should recognize this as being our SR latch. This is the SR latch that we talked about in the previous video. The operation is exactly the same. These three gates over here are the additions to this latch that make it a D latch. So let's talk about how it works. A D latch has these two inputs over here, the D input, which stands for data, and then the E input, which stands for enable. Consider first what happens when the enable input is low, when enable is off. These two AND gates are going to be off. They have zeros coming in, so nothing's going to be able to come out. That means that S and R, in our SR latch portion of this circuit, are also going to be off. They're going to be low. And that means that the circuit is going to hold whatever value it had in the previous configuration. So it's going to be storing. It's going to be holding its configuration. So when enable is low, that means I cannot change the data that this circuit is storing. Now let's consider what happens when enable is high. These two AND gates now have the potential to work. So now the data signal can be either high or low. If the data signal is high, this AND gate will be on. If the data signal is low, this AND gate will be on. These two AND gates cannot both be outputting true at the same time. There is no possible way for these AND gates to both be outputting ones at the same time because of this inverter. That's a very important point because that helps us avoid the condition of the SR latch that we did not want to be in, right? S and R should never be 1 at the same time. These two AND gates ensure that that can never happen, that we will never enter that undesirable state. So then what actually does happen? Well, if E is high and D is also high, this AND gate will be active. That means the set input will be high and the R input will be low, and the output of this circuit down here at Q will be high. It will be 1. We will set the SR latch. If E is high and D is low, then this will be low, this AND gate will be off, this AND gate down here will be on and outputting true, which means our reset bit is high, which means that Q will be low, Q will be off. Then the enable signal can go low at that particular point, and this circuit will remember what the previous value of D was. Whatever D was when the enable signal went low is what will be stored in this particular latch. So that's how a D latch works. Let's take a look at a truth table that kind of shows us in more detail what's actually going on here. So you can see exactly what I just described. D only matters if the E bit is high. D only matters if enable is on. If enable is low, then I don't care what D is. D can be anything that I want. It's just going to remember whatever was previously stored in that configuration when the E bit was high. Okay, so this is a D latch, and actually, while this is solves some problems, it's not quite enough for our storage needs. So eventually we're going to be building larger circuits, and these circuits are going to need to be synchronized somehow. They're going to need to be, working. The timing is going to have to be synchronized so that all of the pieces work at the same time. They work together. So we need something to help us accomplish this. A D flip-flop is going to make our lives a lot easier when we start working with these more complex, more synchronized circuits. You can see that a D flip-flop is simply two D latches wired together. That's it. So we just saw these two D latches. There is an inverter down here as well. Let's take a look at how this actually works. We've got our two signals, D and clock. Okay? So if our clock signal is going to act as our enable, notice that only one of these D latches can be enabled at any given time. So if this clock signal is high, for example, that means this D latch over here on the left-hand side the enable is going to be low. That means we're not going to be doing anything with this latch. It's just going to be outputting whatever its previous value was. That's it. But over here, this D latch will be active. That means that it can read in whatever's being stored in this D latch on the left and output it. And then when the clock switches, when the clock goes low, what's going to happen? Well, this D latch will now be active. That means it can read in a particular value, right? It can read in a particular value and set the output. But that output is actually not going to make it to this D latch, because when the clock is low, this D latch will not be paying attention to what's coming into its D input. Remember, when enable is low, we don't care what the D input value is. We're ignoring it entirely. We're just outputting whatever our previous value was. So when does the value come over here? Well, there's a very important part of the clock cycle for a D flip-flop. The only time that the output of this D flip-flop can change is when the clock signal goes from low to high. Consider what happens when the clock signal starts out as being low and goes high. When it's low, that means this D latch is not accepting any new inputs, but this D latch is. So it's going to read in whatever D is and start outputting it. As soon as this clock signal goes high, right, this latch is going to shut itself off. It's going to remain stable at whatever that value of D is, and then this D latch over here is going to read in that value of D and store it for itself. Right? So only at that point in time, only at the point in time when clock goes from low to high, will this D flip-flop be able to change its value. We call that the rising edge. A D flip-flop always activates on the rising edge, and that's very important. Let me show you, here is a clock signal. Here is a typical clock signal. Exactly what I'm talking about. In previous versions, when we were just talking about the latch, right? The output of a latch can change anytime this signal is high across this entire portion of our clock. The output of that latch could change. That's a long period of time. That's, half a clock cycle. This clock cycle is meant to synchronize things, so we want things to happen at very specific points in time. So by allowing things to only happen on the rising edge, we've now restricted all changes in our latches and our flip-flops to happen at this very short, almost instantaneous moment in time. So we now have a very distinct, very subtle, very specific synchronization point for our circuits. It's very important. Let's go through an example just to illustrate the difference between a latch and a flip-flop. Here you see a slightly different circuit diagram for latches and flip-flops. Over here on the left, this is our latch. This is our D latch. Here's D. This input has actually been relabeled to be called C for clock, right? Over here is our flip-flop. This is our D flip-flop. Again, you see our D input. Again, we have C for clock. The only difference between the two is this little arrow right here. Whenever you see this little arrow on a circuit diagram, that indicates that it is a flip-flop as opposed to a latch. So let's say that I give you a clock cycle that looks something like this, and this timing information for A. Here is information for our A signal over time. Notice A is being fed into both the latch and the flip-flop. The question then becomes, what is the output of the latch and what is the output of the flip-flop over time? Well, let's take a look at what happens. Nothing can happen to the latch unless the clock signal is high. Right? So when the clock signal is high here, we expect the latch to be low since A is low. But then over here in this section, this next clock cycle, we see that when the clock is high, A is also high. So at that point in time, I would expect the output of the latch to also be high. And now we can take a look at the next time the clock cycle goes high. Over here, we notice that A hasn't changed, so the output of our latch doesn't need to change. And then finally, we get over here to this next portion of the clock cycle. We see that A has now gone low, So correspondingly, our latch output will go low. And then finally, when we look at the last two clock cycles, we see that A hasn't changed at this clock cycle, so nothing's going to happen to our latch output at that point in time. And then finally over here, during this clock cycle, we see that the output has gone high again, so the output of our latch will also go high once again. For our flip-flop, things are a little bit different. We don't have to look at when the clock is high, we have to find the rising edges. So we have to find the points in time when the clock signal is going from low to high. So that first point is right here, and we see that the value of A is low, which means that the initial value of our flip-flop is also going to be low. The next rising clock edge is here, and we can see at that point in time A is high, so I would expect the output of my flip-flop to go high at that particular moment. Notice the difference. Notice there's a significant delay between when the latch output went high and the flip-flop output went high. That's due to the fact that the flip-flop only cares what's happening on the rising edge. The next rising edge is right here, and we see that the output has gone low again, so the flip-flop will correspondingly go low. The next rising edge is here. We see that the output is still low, so nothing's going to change. And then finally, at this last rising edge, the output is high, so we expect the output to go high again. Hopefully from this example you can see that in some ways latches and flip-flops behave very much the same, but in other cases they differ significantly. In fact, this case right here illustrates the primary difference between the way latches and flip-flops operate. In the next video I'll talk to you about how we can use flip-flops in larger, more sophisticated circuits.